Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on SSB. So in the last session we discussed about DSB problems. So now we are in SSB. So what is the full form of SSB? SSB is nothing but single sideband. So this all come under the category of amplitude modulation. So amplitude modulation is subclassified into DSB, SSB. Okay. So SSB means having only single sideband. Okay. So this topic come under module 1. So module 1 is covered by course outcome 1. So the first course outcome is outline the basic concepts of communication system, need of modulation, and fundamental elements to realize amplitude modulation systems. So in this module, we covered what is modulation, why need modulation, what are the elements in communication system, and what are the different types of amplitude modulation systems. Okay. So now we are going to solve some numerical problems in SSB. So SSB is developed for the saving power. So it reduces the power consumption. It requires less power than the amplitude modulation system. Okay. So this is the first problem. So in this problem, consider a two-stage SSB modulator with input signal consists of a voice signal in a frequency range of 0.3 to 3.4 kHz. The two oscillator frequencies are F1 100 kHz and F2 10 MHz. So in this problem, following parameters are going to find or calculate. So the first one is sidebands of DSB-SC wave modulated. The second one is the sidebands of SSB modulated waves at outputs of 2 bpfs. The passbands and guard bands of 2 bpfs. So first you will know how to generate SSB. So in this picture we are showing what two-stage SSB modulator. So it means you're having two stages. What is the first stage? Here, you are going to generate SSB by using DSB-SC. So what is DSB-SC? Double sideband suppressor carrier. So that means here in DSB, we are going to suppress the carrier only. The two sidebands are passing as usual. Okay, so that's why here I am using DSB-SC signal. From the DSB signal, we are going to generate SSB. So here we use product modulator and bandpass filter. So we know that how to generate DSB. So DSB-SC is nothing but we are going to multiply the message signal with the carrier. So here F1 is nothing but one of the carrier. So one of the carrier. So just multiply these two signals. What are the two signals? M of t and C of t. So now the generated one is the DSB-SC signal. This DSB signal is passing through bandpass filter. The required SSB is generated. So the output of a bandpass filter is SSB. But in this problem, they given two stage. So that's why here we're using two product modulators and two bandpass filters. Okay. So this is a brief discussion about this problem. Now what are the given data? And by using the data, we are going to find these sidebands and passband, guard band of these bandpass filters. Okay. So here the given the frequency range of the voice signal means it is nothing but the message signal. So FM frequency range is 0.3 to 3.4 kilohertz, and the oscillator frequencies is nothing but FC1 and FC2. So FC1 is 100 kilo, F2 is 10 mega. Okay. So in the next slide, we are going to write the given data, then start the problem. Okay. So here F1, that means the first carrier is a 10 kilo, F2 is the second carrier, it is a 10 mega, and the message signal is starting from 0.3 to 3.4 kilohertz. So here we are using the two stage. So the first stage is a product modulator with carrier, a product modulator with a band pass filter. Okay, so the product modulator having a carrier signal. Okay, so here we are going to find the LSB of the first product modulator. So PM1 is the product modulator 1. So the output of product modulator 1 consists of two bands, two side bands. What are the two side bands? One is the lower side band and another is the upper side band. Why? First we are going to generate the DSB signal and passing this DSB signal through a band pass filter, then we are getting the SSB signal. Okay. So what is LSB? LSB is nothing but FC minus FM. Already we know. So here we taken 100 kilohertz. This is FC minus, what is our FM? 0.3 kilohertz to 3.4 kilohertz. So 0.3 kHz to 3.4 kilohertz. So this is my LSB. Okay, 100 kilohertz minus 0.3 and 100 minus 3.4. So here the LSB is 99.7 kilohertz to here 96.6 kilohertz. This is my LSB. Now USB. USB nothing but FC plus FM. So what is FC again? 100 kilohertz plus what is FM? 0.3 kilohertz to 3.4 kilohertz. So this is my FM. So now adding, that is nothing but 100.3 kilohertz to 103.4 kilohertz. So this is my USB. One is LSB and another is the USB. Okay. So the USB range is 100.3 kilohertz to 103.4 kilohertz. Now here S1 of t. Why? This is my DSB signal. Here I am considering. So in the first stage, we can say M of t is multiplied with C of t, then produces DSB signal. This DSB signal is passing through band pass filter. Then we got this S1 of t. S1 of t is nothing but SSB signal. Okay. So now S1 of t signal is nothing but 100.3 kilohertz to 103.4 kilohertz. Now by using this S1 of t, we are going to the second stage. The second stage contains of again product modulator 2 with a combination of band pass filter. Okay. So here coming to the next slide, product modulator 2. Here I am considering product modulator 2. So the product modulator 2 is having LSB and USB. So here S1 of t, first you go to write S1 of t is 100.3 kilohertz to 103.4 kilohertz. This is my S1 of t. Okay. So here what is the FC? FC is nothing but 10 megahertz. Okay. So this is my FC. Why? For the second stage product modulator, FC F2 is the 10 mega. So it's nothing but carrier frequency. So LSB is FC minus FM. So 10 megahertz minus 100.3 kilohertz to 103.4 kilohertz. So now 10 megahertz minus this 100 kilohertz. So what you got? 9.8997 megahertz to here we are going to second one is 9.8966 megahertz. So this is my LSB. Next one is USB. So USB is nothing but FC plus FM. So 10 megahertz plus 100.3 kilohertz to 103.4 kilohertz. Okay. So now we're going to add this 10.1003 megahertz to 10.1034 megahertz. So this is the two product modulators LSB and USB. Now we know the guard band. So guard band is defined the highest frequency component of the LSB to the lowest frequency component of the USB. So this is the lowest frequency component of the USB, and whereas the highest frequency component of this LSB. So highest frequency component of LSB is this one. So this is the range. What that one? 99.7 kilohertz to 10.1003 megahertz. Okay. So guard band of band pass filter 1 is 99.7 kilohertz to 100.3 kilohertz, and guard band of band pass filter 2 is 9.8997 megahertz to highest is 10.1034 megahertz. So this is the highest and the before one is the lowest. So this is the guard bands of both the band pass filters. Okay. Now coming to the second problem. So an SSB or a SSB transmission contains 10 kilowatt. This transmission is to be replaced by a standard amplitude modulated signal with the same power content. Determine the power content of the carrier and each of the sidebands when the percent of modulation is 80%. So here the given data is P. So power the given is 10 kilowatt and percentage modulation, that is nothing but mu or m. You can take any one. So 80% is 0.8%. Okay. So here the transmitted power is PT for SSB. So here you can take it as PT, or it is equal to PSSB is equal to 10 kilowatt. This one they given. Okay. So let us start the problem. So total power is equal to carrier power plus LSB power plus USB power. One is carrier power, one is the lower sideband power, upper sideband power. So we know that PC is equal to PC mu square by 4. Again the same power, mu square by 4. So this is PC plus, so we can take the common, PC plus mu square by 4 plus mu square by 4. So mu square by 4 plus mu square by 4, 2 mu square by 4. So the output is mu square by 2. So PC 1 plus mu square by 2. So what is the mu value here? Mu value is 0.8. So PT is equal to PC into 1 plus 0. Square divided by 2. So 0.8 square is 0.64. So PC 1 plus 0.64 divided by 2. So nothing but this value is PC into 1.32 PT. Why here 0.32? 1 plus 0.32 is equal to 1.32. So it is PC. Okay. So now required PC. So PT divided by 1.32. So what is PT? PT is given as 10 kilowatt. So 10 kilowatt divided by 1.32. So by using calci, we get the answer. That is 7575.76 watts. So this is my carrier power. Okay. So here the power content of the sidebands is equal. So the difference between the total power and the carrier power is PSB is equal to PT minus PC. So already you know that PT is 10 kilo. So 10 kilo minus 7575.76. So this is sideband power. So that is P USB plus P LSB. So that gets the PSB. Upper sideband plus lower sideband. That is the two sideband power. These two are equal. So here P USB is equal to P LSB is equal to here 10,000 minus 7,575 minus 76. So its value is 24.24 divided by 2. Then we got 12.12 watts. So this is the each sideband power. That means lower sideband power and upper sideband power is equal. 112 watts. Okay. So coming to the third problem. Consider a baseband signal M of t containing frequency components at 100, 200 and 400 Hz. This signal is applied to an SSB modulator together with a carrier at 100 kHz with only the upper sideband retained. In the coherent detector used to recover M of t, the local oscillator supplies a sine wave of frequency 100.2 kHz. So determine the frequency components of the detector output. So here the baseband having three frequency components. One is 100, 200, 400. Okay. So this baseband signal is applied to a SSB modulator and the carrier having 100 kHz. Okay. And here only upper sideband. Why? Because SSB means single sideband. If single means either upper or lower. But in this problem, they given as upper sideband. Only with upper sideband. Okay. So Here we go to write first m of t. M of t is nothing but message signal. So that is cos 2 pi f1t plus cos 2 pi f2t plus cos 2 pi f3t. Why? Because they given three frequency components 100, 200, 400. That means the first one is 100 Hz, F2 is 200 Hz, F3 is 400 Hz. So F1 is 100 Hz, F2 is 200 Hz, and F3 is 400 Hz. Okay, these are the frequency components. So the time domain expression for the SSB with only upper sideband returned. Okay, so we are going to write this SSB of t. So this is time domain for the SSB signal with only the upper sideband. Okay, so that is AC by 2 of cos 2 pi f1t plus cos 2 pi f2t plus cos 2 pi f3t into cos 2 pi fct. So in these brackets, within the bracket we are having three frequency components, three message frequency components, and outside the bracket is carrier cos 2 pi fct. Okay, and minus AC by 2 sine 2 pi f1t plus sine 2 pi f2t plus sine 2 pi f3t into sine 2 pi fct. So this is the upper sideband, SSB with upper sideband. Okay. Now simplify this expression. AC by 2 cos of 2 pi f1 plus fc or fc plus f1, no problem. But general taken the higher frequency term, so fc, and this one is f1 of t cos of plus cos of 2 pi fc plus f2 of t of cos of 2 pi of fc plus f3 of t of cos. So this is upper sideband. Okay, SSB with upper sideband. Now the output of this expression passing through the coherent detector. So the output of the coherent detector. So this SSB signal is passing through a coherent detector. Now what is the output of this coherent detector? Okay, this is a SUSB, single sideband with only USB. So here we would write the output of the coherent detector is given by Y of t S USB of t into C of t. Why? Because in this problem second carrier is given at the coherent detector. So before going into this problem, first you know the meaning of the coherent. What is the meaning of coherent detection and what is the non-coherent? So coherent detection means here the phase information is similar as used at the transmitter. That means you are going to detect the signal with the same phase reference whatever the transmitter is used. That we can call as coherent. Same phase information is used to recover the message signal. That means both transmitter and receiver using the same phase information. clearly here you can say that is a phase synchronization. That means we are using the phase synchronization. Such type of detection can be called as coherent detection. Okay. So now, what is my USB? In the previous slide, right, written as AC by 2 cos of 2 pi of Fc plus F1 of T of plus cos of 2 pi of Fc plus F2 of T of plus cos of 2 pi of Fc plus F3 of T of. So this is my USB. This USB sideband, single sideband is multiplied with the C of T. So what is C of T? Carrier, that is cos 2 pi Fc dash of T. So this Fc dash indicates the at the detection using the same phase information. Okay. So where Fc dash is given as 100.2 kilohertz. So that is Fc plus delta F. So Fc is 100 kilo plus 0.02 kilohertz. So this is Fc dash. So the LPF of the coherent detector removes the sum terms and allows the only the difference terms. That means it allows only the different terms. What is the different terms? Difference term means low frequency component. Sum term means it is goes the high frequency terms. So generally the L-pass filter which allows the low frequency terms and attenuates the high frequency terms. So high frequency term is going to attenuate it. Okay. So M dash of T is equal to AC by 4 cos of 2 pi F1 minus delta F of T plus AC by 4 cos of 2 pi F2 minus delta F of T plus AC by 4 cos of 2 pi F3 minus delta F of T. Okay. So this is my M dash T. That means the output of the detector. Why? This total Y of T is passing through the detector. So the detector also having LPF. So the LPF which allows the low frequency terms, that is the difference terms. Now what are the F1 minus delta F, F2 minus delta F? Here we are going to see. Okay. So here F1, that means frequency components at the detector output. F1 is equal to 100 minus 0.02 kilohertz. So this is F1 minus delta F. Sorry, F1 minus delta F. In the brackets, F1 minus delta F. So writing clearly, F1 minus delta F. So F1 is 100 Hz. Here delta F, the deviation is 0.02 kilohertz. So it is nothing but 20 Hz. So here got 80 Hz. F2 minus delta F. F2 is 200 minus 0.02 kilohertz. So what do you get? 200 minus 20, 180 Hz. F3 minus delta F. So F3 is 400 and the deviation is 0.02 kilo. Again 400 minus 20. So 380 Hz. 380 Hz. Okay. So this is the answer. So the fourth problem is A received single tone sinusoidal modulated SSB signal cos of 2 pi of Fc plus Fm of t has a normalized power of 0.5 whole square. The signal is to be detected by the carrier reinsertion technique. Find the amplitude of the carrier to be reinserted so that the power in the recovered signal at the demodulated output is 90% of the normalized power and neglecting the DC component. Okay. So this problem also belongs to the SSB, single sideband suppressor carrier, simply SSB signal. Okay. So here for single tone means we are using only one message signal, only one modulating frequency. It can be also called as single tone. We are using only one message signal frequency. Okay. But here they are using the carrier reinsertion technique. Okay. So for a single tone SSB signal, the waveform after the carrier reinsertion becomes S of t is equal to AC cos 2 pi FCT plus cos of 2 pi of Fc plus Fm of t. This one. This is AC plus cos 2 pi Fm t. This one. Whole brackets of cos 2 pi Fct minus sine of 2 pi Fmt into sine 2 pi Fct. So here cos of A plus B is going to apply. So that is cos A cos B minus sine A sine B. So in the second term, first term is AC cos 2 pi Fct. So this is AC cos 2 pi Fct plus cos of 2 pi Fc plus Fm of t. So here two terms. One is the carrier frequency and one is the message frequency. So we can treat as cos of A plus B. So cos A cos B minus sine A sine B. Okay. So the output of demodulator is you can treat as E of t. So E of t is equal to AC plus cos of 2 pi Fm of t whole square. This whole term is going to square plus here sine of 2 pi Fmt whole square. So sine square 2 pi Fm of t and this whole is taken as 1 by 2. So this is the output of the demodulator. Okay, output of demodulator, we are considering the amplitude of this term. Okay, so here A plus B whole square. Again, in the square root, this is the whole square root. So the first one is A plus B whole square formula you can apply. That is A square plus B square plus 2AB. And another one is the sine square term. Okay. So here you can write AC square plus 2AC cos 2 pi Fmt and again cos square term, cos square 2 pi Fmt. So A square plus 2AB plus B square plus sine square term, sine square 2 pi Fmt. Okay. So what happens? Sine square theta plus cos square theta is nothing but 1. So this whole term is going to 1. So the output of the demodulator we can write as AC square plus 1 plus 2AC cos 2 pi FMT. So this is the demodulator output. So here we can take common, this is square root of AC square plus 1, the first term, which leads to AC square plus 1, the bracket of 1 plus 2AC divided by square root of AC square plus 1 into cos 2 pi FMT root, or you can write 1 by 2. Okay. So coming to the slide. So continuation of this previous one. AC square plus 1 of 1 plus AC cos 2 pi FMT divided by AC square plus 1. So we are removing this square root term within the bracket. Okay. So the approximately equals to square root of AC square plus 1 plus AC square plus 1 plus AC cos 2 pi FMT divided by square root of AC square plus 1. So here neglecting the DC component. So they given the problem, neglect the DC component. So of neglecting DC component, the normalized power which is equal to 1 by 2 AC divided by AC square plus 1. So this is the normalized power. But this normalized power is equating with the modulating, okay, depth of modulation or modulation index, whatever it may be. So in order that the recovered signal at the demodulated output is 90%. So my mu is equal to 90%, 90 by 100 is given to 0.9. Okay. So 1 by 2 AC square divided by AC square plus 1 divided by 0.5, which is equal to 0.9. So this 2 goes to cancels. So AC square by AC square plus 1 is equal to 0.9. So cross multiply. AC square is equal to 0.9 of AC square plus 1. So here 0.9 AC square plus 0.9. So this side is AC square. So move this AC square minus 0.9 AC square, which is equal to 0.9. So here AC square is common. 1 minus 0.9, which is equal to 0.9. So nothing but 0.1. So AC square is equal to 0.9 divided by 0.1. So it is nothing but 9. So AC square is equal to 9. Then AC is equal to 3. So the amplitude of the reinserted carrier should be 3 volts. So this is the amplitude of the carrier. So after carrier reinserted, what is the amplitude? Required amplitude is 3 volts. Okay. So coming to the another problem. So the fifth problem, this one. So the fifth problem is calculate the total power in case of SSB technique. A 500 watts carrier is amplitude modulated to a depth of 75%. How much power is achieved for SSB compared to AM and DSB SC? So here the given data is PC, carrier power is 500 watts and mu also. Okay. So the mu is 75%. So 75 by 100, 0.75. This is my new value. So they given PC carrier power, they given modulation index. So by using this, we are going to calculate the total power and comparing with the AM and ASBSC. Why? Because AM means double sideband with full carrier. So the first case carrier will be allowed, whereas in second case DSBSC, two sidebands will pass but suppressing the carrier. And coming to the SSB, only one side. SSB means only one side, either upper side or lower sideband. Upper sideband or lower sideband. Any one sideband can allow. So that is the SSB. Okay. So here the required formula PT is equal to PC into 1 plus mu square by 2. So this is the required formula. So in this formula they given PC, carrier power is given and mu value is given. So let us substitute how much a total power. Okay. So PC is 500 watts into 1 plus mu square, 0.75 square divided by 2. So by using calculation, 0.75 whole square value is 1 plus 0.6 by 2. So nothing but 2. Here 3 terms, that is 500 into 1.3. So this is my PT. So multiply this, you got 650 watts. So the total power is 650 watts with the carrier power 500 watts and the modulation index value is 0.75. Okay. So power saving of SSB with respect to AM. Okay. So the first PT minus PSB divided by PT. So here we calculate this PT, total power calculated in AM. Now sideband. So for PSB, power in sideband. So having the formula PC mu square by 4. So what is PC? 500 mu square. That is mu square. So mu value is 0.75 square divided by 4. So how much? 75 watts. Okay. And power saving. So this is power saving. Power saving. So we know that the PT, we know the PSB. So just substitute. So power saving is equal to PT 650 watts minus 75 divided by 650. So how much power is saved? 90%. This is 90%. So power saving in DSB or first you got to find the total power. Total power in DSB. So DSB means two sidebands. Here already you calculated one sideband power. So two sideband means 2 into PSB. So 2 into 75, 150 watts. Okay. Now power saving with respect to DSB. So we are comparing SSB with DSB. Okay. So power saving in SSB with respect to DSB. So same formula. So here the PD, total power in DSB is 150 minus 75 divided by 150. So here giving 50%. So the power saving with respect to AM is 90% and the power saving in SSB with respect to DSB is 50%. Okay. So these are the values. Okay. For this problem. Coming to another problem. So 6.1. Find the percentage power saving when the carrier and one of the sidebands are suppressed in an AM wave modulated to a depth of 100% and 50%. Okay. So why? Because this AM, DSB, SSB both are coming in this module. So here we are considering this problem. Okay. So the first one, in first case, the mu value is 100%. So 100% means mu value is 1. 100 by 100 gives 1. So mu value is 1. Okay. So the total power in AM. So what is the formula? PT is equal to PC into 1 plus mu square by 2. So this one. So here mu value is 1. So 1 by 2. So here you can written as 1 plus 0.5 or 1.5 PC. So PT is equal to 1.5 PC. And sideband. Okay. So one of the sideband. So PSB. PSB is equal to same formula PC into mu square by 4 as usual used in the previous problem. Sideband is PC into mu square by 4. So first PC. So PSB is equal to here mu value is 1. So 1 square is 1. 1 by 4 0.25. So in this case 0.25 PC. So this is sideband power. Now power saving. So power saving. So that is formula is PT minus PSB divided by PT. Okay. So here what is PT? PT is 1.5 PC minus PSB 0.25 PC divided by 1.5 PC. So 1.5 minus 0.25. Okay. So what do you get? 1.25 PC divided by 1.5 PC. So this PC going to cancel and 1.25 divided by 1.5. So how much power saving? So the power saving is equal to 83.3% when mu value is equal to 1. So this is the first bit. In this problem another bit is also there. That is 50%. Mu value is 50%. Okay. So here mu value is 50%. So 50 by 100 that is equal to 0.5. So as usual taking the total power. This is the second problem. So total power. So PT is equal to PC into 1 plus mu square by 2. Okay. So here mu value is 0.5. So PT is equal to PC into 1 plus 0.5 square by 2. So 0.5 whole square is 0.25. So divided by 2. That is 0.125 you got. So 0.125 plus 1 it is 1.125. So 1.125 PC. This is the total power. Now sideband power. Sideband power. So sideband power is equal to PSB which is equal to PC mu square by 4. So PC, what is mu value? 0.5 whole square divided by 4. Again 0.5 whole square is 0.25 divided by 4. So it is nearly 0.0625. So 0.0625 PC. So this is PSB. So again power saving. So power saving formula is PT minus PSB divided by PT. Okay. So now we're going to substitute 1.125 PC minus 0.0625 PC divided by 1.125 PC. So using calci, you can calculate the output of this sum. Okay. So here the answer is 94.4%. So this much power is going to save. So for the first bit is 83.3 and the second bit is 94.4%. Okay. So another problem is calculate the power transmitted if it is transmitted as SSB for AM transmitter of 1 kilowatt power is fully modulated. So fully modulated means here mu is 1 fully. Mu is 100%. So 100%. So mu is 1. Okay. So calculate the power transmitted. So same formula. PT is equal to PC into 1 plus mu square by 2. So here PT is 1 kilo and mu value is 1. Okay. So mu equal to 1. So let us substitute PT equal to PC 1 plus 1 by 2. So it is 1.5, or you can take it as 3 by 2 or it may be. So PT is equal to, you can write another one, 3 by 2 PC. Okay, 3 by 2 PC. So what is PT? So PT is 1 kilowatt. So PC is equal to 2 by 3 kilowatt simply. So this is my PC. So now the total sideband power in the AM signal. The total sideband power in the AM signal is, here you can write total sideband power. So total sideband power in AM signal, is equal to 1 minus 2 by 3. Why? Because you go to subtract from the total power. Why? PT is equal to PC plus 2 sideband powers. Previously discussed it. PT is equal to PC plus LSB plus PUSB. So this is the sideband power. So here I required this sideband power PT. So this power I required. So what happens? PT minus PC. So what is PT? 1. 1 watt. 1 kilowatt minus this 2 by 3 kilowatt. So what is given? 1 by 3 kilowatt. So power in each sideband. Why? Because these two sideband powers are equal. PLSB, PUSB having the same power. So in each sideband means here 2 into PSB is equal to 1 by 3. So PSB equal to 1 by 6 kilowatt. 1 by 6 kilowatt. So this is the problem for this 7th one. Okay. So the 8th one is using Hilbert's transform. There are the equations for SSB signals. So here we are going to derive the SSB signal for SSB signal using Hilbert. So we are having one way how to produce SSB signal. Here just we are passing the DSP signal through a band pass filter. Then we get to SSB signal. Okay. So in this way we are going to derive this SSB signal. Okay. So first we required the DSB SC of T. So this is the time domain of DSB. So how to get the DSB signal? Just you go to multiply the m of t with c of t. Okay. So AC m of t into cos 2 pi FCT. Here AC cos 2 pi FCT is nothing but C of t. M of t is the message signal. C of t is the carrier signal. So when you go to multiply these two terms, it will produce DSBSD signal. So this is a time domain description of the DSB signal. That is nothing but C of t into M of t. Okay. So the low pass complex envelope of the DSB signal modulated wave can be expressed as, so this is a low pass complex envelope of the DSBSC signal is simply AC M of t. Okay. So you have a doubt. SSB we are saying. So which sideband we are finding here? So generally we go for the upper sideband. So in this derivation we are using the upper sideband. Okay. So I am considering the upper sideband only. So this upper sideband contains both the in-phase components and quadrature components also. Okay. So here we are having both in-phase and quadrature components. So then yes till u of t. So here I am using upper sideband. So it indicates, u indicates upper sideband. So SU of t is the complex envelope of SU of t. So the still function indicates the complex envelope. Okay. So this is the complex envelope of SU of t. Complex envelope of SU of t. So what is SU of t? Here you can return or rewrite this. The real part of S tilde of U of t exponential j2 pi FCT. So this is taken as the equation 1. So first you go determine this S tilde U of t. You go determine S tilde U of t. So in two ways you will determine this S tilde of U of t. What one? The first one is the bandpass transfer function. Here to determine S tilde U of t, the first one is the bandpass transfer function. Why? First we generate the DSP signal. So this DSP signal is passing through a bandpass filter. So I require the transfer function of that bandpass filter. Okay. So the bandpass filter transfer function HU of F is replaced by an equivalent LPF transfer function. So this is H tilde U of F. Generally, we are passing DSP signal through a bandpass filter. Here I am replacing this bandpass filter with an equivalent of LPF. So H tilde U of F, which represents the transfer function of low pass filter. Okay. So H tilde U of F is equal to 1 by 2 of 1 plus signum function of F, and otherwise 0. So here the frequency range is this one. Remaining is otherwise. So this is the transfer function of the equivalent low pass filter, where SGN of is signum function. Okay. The DSBSC signal wave is replaced by its complex envelope. So the spectrum of this are not required. The spectrum S DSB SC of t is equal to AC M of F. So we are written this one. So here in the time domain DSB signal. Here the time domain complex envelope. Here the complex envelope of DSB signal is written as AC M of T. In the frequency domain, this is S tilde DSB SC of F. So this is F. F indicates the frequency domain. So that is AC into M of F. In the time domain, just it is AC M of T. Okay, why? How to generate DSB signal? Just to multiplying the carrier signal with message signal. Okay, so that's why the frequency domain also contains AC into M of F. So this is the second one and this is the third equation. Okay, now the desired complex envelope S till U of F is determined by evaluating the IFT, inverse Fourier transform of the product of H till U of F and S till DSB SC of F. So this one is this one and another one is the signum function where this one. So IFT of both these H till U of F and this S till DSB SC of F. Okay. So this one is IFT of H tilde U of F S tilde DSB SC of F. So this is the fourth equation and here this is the time domain S tilde U of T, which is equal to inverse Fourier transform of H tilde U of F S tilde DSB SC of F. One is the transfer function and another one is the DSB SC. Why? Because here we are getting SSB when you go to pass DSB signal through a band pass filter. Here this is the filter response. Here generally this is band pass filter, but this band pass filter is replaced by the equivalent LPF. So this is LPF transfer function and this is the DSB signal. So you are going to both this IFT, then you get this time domain of SU of T. Okay, so you got to substitute this H tilde U of F value and S tilde DSB SU of F value. Okay, so S tilde U of T, which is equal to IFT of, here the first one is a transfer function. This is signum function 1 plus signum function of F into AC M of F. Okay, so again IFT of AC by 2 of M of F plus signum function of F into M of F. So the big bracket. Okay, so S tilde U of T, that means upper sideband of SSB signal, which is here AC by 2 put outside. Here inverse Fourier of M of F, just M of T as a signum function inverse. So it is a complex value get J M cap of T. So this is my fifth equation. Okay, so now substituting this fifth equation in equation 1, you get S U of T. Okay, so this is a tilde function. So but I not required as tilde function. So S U of T is equal to the real part of S tilde U of T exponential J2 pi FCT. So this is question 1. So substituting equation 5 in this 1. So this is equation 1. So I'm going to substitute equation 5 in equation 1. Okay. So then S u of t, which is equal to real part of AC by 2 into m of t plus j m cap of t into e power j 2 pi fct, j pi 2 pi fct. So by solving all this, the values, you got in phase and quadrature terms. So you are going to get the in phase and quadrature terms. So SU of t, from this you get AC by 2 of m of t into cos 2 pi fct minus m cap of t sin 2 pi fct. So this is the in phase component and this is quadrature component. So two components. This SU of t contains, one is in phase, another is the quadrature component. Okay. Okay. Thank you. And the references, this content of information taken from Summer Hacking and Analog Communications by Chakrabarti. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.